Okay, it's my great pleasure to welcome my friend, mentor, and collaborator from Trieste, Ludwik Dąbrowski, New Equivariant Dimension. The floor is yours, take it away.
Thank you, Piotr. So I should excuse myself for my coarse voice, with which I will present, but only roughly, the work package number 5. And I will start with a very basic and known to all topologists theorem in topology, its surroundings and also some generalizations. Namely, this is about Borsuk-Ulam Theorem. And in all my talk, spaces, if there will be spaces, will be Hausdorff, and maps will be continuous. Sn is a unit sphere in Rn+1, Bn is a unit ball in Rn, and for any n, sigma is the antipodal, so for any sphere is antipodal involution of n-dimensional sphere. Then there are at least 2, 5 or 6 equivalent statements of Borsuk-Ulam Theorem. I will present only 2. Is that there is no map from Sn to Sn-1, which commutes with this antipodal involution. And there is no map from the ball and dimensional ball to its boundary and minus one dimensional sphere, which commutes with the antipodal involution on the boundary. Well, of course, such antipodal involution generates a free action of a group Z modulo 2Z, integers modulo even integers, on a sphere, on any sphere, and we shall call such a map variant for brevity if we know what is the group of which we ask for the equivariance. If it commutes with this involution, antipodal involution, with this generator as with this. This theorem has different proofs, a lot of applications, various equivalent theorems, plentiful of corollaries, and some of them are fun facts, which I will not mention today. But also, in particular, from this statement number 2, you see immediately that also a version equivalent statement of the Brouwer fixed point theorem for maps from balls to balls is that there is no map from ball to its boundary, which is identity on the boundary, since identity is, of course, equivariant map with respect to the antipodal involution. Which means that as any sphere is not a rectangle of a corresponding ball, or I will call them that the sphere is not contractive. Okay. Obviously, the two-element group Z modulo 2Z is also contractive, since it is not connected.
Ludwig, I'm sure there is such a word as obviosity.
Yeah, I think I checked on the Webster. I think on one of these I checked obviosity. Yes, should be.
You're right, obviosity, the quality of being obvious. Wow, I'm impressed. Obviosity. Okay, good.
So with Paul Baum and Piotr Hayats, we formulated a generalized Borsuk-Ulam conjecture, which is so-called classical part, and then we have also quantum conjecture. In terms, it is done in terms of topological join of 2 spaces. In particular, we'll be interested only if one of the spaces is a group, but let me define we call you the definition of a join as the product of space X, Y, and interval, a segment from 0 to 1, which here we collapse, so modular relation generated by collapsing, and there are various conventions. At this edge, I collapse, for instance, X, so the only point of Y survive, and at the other edge, I collapse the space Y. Then this classical conjecture is as follows: if X is a compact space with a free action of a compact non-trivial group, okay, then for the diagonal action of G on the topological join, so diagonal is that you act here and there on G, you act by right multiplications of the group. there is no G equivariant map from the join X with G to the space itself. And this is indeed a generalization of the theorem, actually of theorems, this structural generalization, since join of n-dimensional sphere with two-element group Z modulo 2Z is a minus n+1 dimensional sphere actually, okay? So it's a generalization. And here I just draw by hand some of the corollaries. So here you see we have this Borsuk-Ulam conjecture. If I just deal with the Borsuk-Ulam conjecture, if I have theorem, I would pick T, theorem. So as I said, there are no equivariant maps for G satisfying this with G, if A actions on X and so on, so non-trivial. There are no equivariant maps from the join to the space. It follows that you have also another, the second version, which I mentioned, the usual standard case for spheres, okay, that it implies that there is no map from the cone of the space X to the space X, which is equivariant on the boundary of the cone on X itself, okay? And also this is equivalent statement, namely, if this is true, it's also this is true, if and only, and also this one implies this one, this can be shown explicitly. From this so in particular, from this version, you have Brouwer versions number, the version which I stated, generalization of the version of Brouwer, theorem for balls, which
sorry, Ludwig, sorry.
No...
Ludwig, may I interrupt for just a second? Yes. So when I look, I'm sorry, I just cannot resist the temptation. When you look at this arrow, which goes from G cross G to G, that's actually equivalence, right? I mean, this implication goes in both ways. I mean, G is non-contractible if and only if G join G is non-trivial PFB. But I have a problem with
okay, here. Okay, so here.
Okay, yeah. But when it comes now go back to the left side. I think, I mean, please correct me if I'm wrong, but I believe you don't really know what is an action on the cone, and I think that the statement is that there does not exist a continuous map gamma sort of retraction, but after you compose this gamma with a canonical inclusion of X into the cone of X, then the composition is not equivariant. I think that's the statement.
Yes.
Yeah.
Also this can...
because I don't think you can extend an action to the cone. Okay. Yeah. So you see that it generalizes the concept of being non-contractible. I mean,
no, but I'm not saying about.
Yeah.
So you say that we should also put some action on the cone.
No. I don't think there should be action on the cone. It's about composition, just like a way of phrasing that the space, there's no retraction, that the space is not contractible, is to say, aha, so I put my space into the cone, and there is no continuous map from the cone back to the space such that the composition is identical. That's really, being non-contractible. And you see, so here we are much more general because the only thing that we demand is that there does not exist such a continuous map, that the composition is equivariant.
Yes.
So this is a much weaker condition than demanding it to be identity, or saying that there does not exist such a composition that we get identity. Of course, identity is equivariant for no matter what action you have.
Yes. Okay, but there is also conjecture, let's say Borsuk, but it follows from this one actually that there is no equivariant map from the join of G, X with G to G. So let me call it the join of X with G is non-trivial principal fiber bundle, because such a map we had global trivialization. Okay. Let me also add that principal fiber bundles are not necessarily locally trivial, so they are trivial fiber bundles in the sense of Cartan principle. Okay. So then it follows that in particular for X equals G, G join G is non-trivial principal fiber bundle, and as Piotr says, equivalent to statement that G is a non-contractible compact. Well, there are some other conjectures which I won't make use today, but let me just flash it that there is some importance of this conjecture, okay, even classical conjecture. Namely, it partially settles in a paper with Kirvazitu and Ludwik Dąbrowski. We settled the conjecture by Ageev that there are no equivariant maps between Menger compacta with free action of non-trivial zero-dimensional compact metric group, which implies so-called weak Hilbert-Smith conjecture for p-adic actions that for any arbitrary prime, the group of p-adic integers cannot act freely on a connected topological manifold M. So this is the weakness condition with dimension M modulo p-adic integers finite. And this actually is to show, or it reduces to p-adic integers, so-called weak Hilbert-Smith conjecture. I think it's stated really like that by the Dranishnikov in a paper which I didn't quote here, okay? We slightly make it stronger by assuming, he assumes that there is a compact group, but we assume also compact G acting freely and properly on a connected topological manifold M, such that the orbit space of this action of G is finite dimensional, must be a Lie group. Of course, this comes from fifth Hilbert problem about identification of Lie groups among topological groups, and big open still not stated, not resolved. Problem number 5 of Hilbert, modified slightly by Hilbert. Borsuk-Ulam conjecture, which I just stated, with conjecture with Paul and Piotr, is actually theorem which is known for finite groups. Actually, you can find using joins in a book, Netherlands special book for this, and joins were there, and theorem is probably not stated like that, but it can be got from the various results in the book. I think it's stated by Passer, by Benjamin Passer, that for any group G which has torsion, so non-trivial torsion, this conjecture is actually true, okay? It holds, so it's a theorem. And in a moment, I'm going to present theorem which is better, so conglomerates these results, namely a stronger and so far best result, which, as far as I know, takes Q from the following statement property that if X and Y are compact principal G bundles, so is the join for the diagonal G action. It's free. I don't know if both are assumed locally trivial. We expect it should be also true for locally trivial principal G bundles, but I think no, it's not yet explicitly written up, no place. So in particular, for any compact group G different from one non-trivial group, join of G with itself is non-trivial principal G bundle over, well, the quotient. Quotient in this case is the suspension of the group G. Indeed, such an equivariant, such a trivialization would be equivariant map from G join G to G, and this would be equivalent, as Piotr said, contraction of G, which is impossible for groups which are non-trivial compact topological groups which are non-trivial. For example, if we take Z modulo to Z, we get join is S1, and this is a non-trivial bundle over projective real space, one-dimensional. U1 is, if we take G U1, then it's just the second of fibration, or first, depending on the count. U1 fibration of S3 over S2, and for SU2 you get fibration S7 over S1. But there is more generally theorem which apparently is we attributed to Bestvina and Edwards, probably between the 70s and 80s, which, as far as we know, we couldn't got even information from Edwards himself. It's unpublished, no place. So we restated it with Alexander Kirvazitu and Mariusz as follows and proved it, okay, explicit proof. For a non-compact, non-trivial group, there are no G equivariant maps from an iterated join n+1 times 2 iteration less 1 iteration. So in particular, this is about this particular situation for the diagonal G actions.
But please correct me if I'm wrong. You improved on the results of Bestvina-Edwards because they had this theorem under some assumptions of a compact quantum group, whereas you have it
but
in
we
full
don't know
generality.
statement of the never seen the statement of the theorem, never seen the proof. So it was just
so it's not on unpublished, it's unpublished and unseen.
Okay. Yes. Okay.
Yeah,
well,
I think
can I have a conference in America mentioned the problem to showing it, solving it for p-adic integers in particular, which is of course not.
Mariusz, you wanted to weigh in.
You know, maybe you can comment.
Mariusz wanted to add something, so.
No, I just wanted to say that,
please.
yeah, that the referee of the paper, he claims that he saw the result of Bestvina and Edwards and that they assumed the group to be metric. And that we improved it to go beyond metric, but.
Okay.
Oh, I see, yes, okay.
But
Yeah,
I also
we know
never seen
this was anonymous referee.
Yeah.
This was anonymous referee, so we don't know who was this.
Yes, how do you know it was not a woman? So you said he.
Well, or
She, he, she, he or she.
Okay. And where did you publish your result, Ludwik, Mariusz?
It's Kyoto Mathematical Journal.
Kyoto. Okay.
Okay, so equivalently to this theorem, I will state two equivalent results, two theorems, or one will be called proposition. But first, I have to define first equivariant dimension, topological dimension. Okay, locally triviality. We shall see that's actually related to this, to the title of my talk, namely G index. So G is X is a G space with actually it's true for any action of a compact group G on a compact space X. We can define the G index of the space X as infimum over natural numbers such that you can find a G variant map from X to n+1 times. And proposition is that the theorem which Bestvina, and we attribute to Bestvina-Edwards, and we have improved it a little and shown, is actually equivalent to the statement that Borsuk-Ulam conjecture is true for spaces with this, for spaces with free actions of G on this space of compact non-trivial groups, whenever G index of this space is finite. And this true proof is, okay, proof of the Bestvina-Edwards is quite complicated. You can find it in the journal, but the proof that this is equivalent to this statement is quite simple. So if we assume the opposite, I try to show that from the Bestvina-Edwards or our follows theorem for Borsuk-Ulam, generalized Borsuk-Ulam theorem, you just proceed by contrary. So assume it's not true, this statement. So we have index. So we have index which is finite, but there is equivalent map from the joint X. So Borsuk-Ulam is not satisfied. Let's assume like that. So X join G to X, which contradicts our theorem. Namely, from n+1, we can go just add here without any problem and join with X and just insert this into G star n+1, which we write as G join G star n. I mean, this is kind of associative split this G join as you want, first or any place, or just write join G n time, n+1 time. Then we use, in this slot, we use this assumption that there is a map, so something which is not we claim is not true in the conjecture in the theorem. So because of that, you go to X here, so and iterate up to going up to X join G, and then again there is such a map. And finally, this X is sitting because of the action, free action in the join, which would be a map which is not allowed, not possible due to the theorem as I just mentioned, Westina and that. There are no such maps. So it's in the direct direction, but in the opposite direction, it's quite clear because just can take for X just G, it's clear from this one. From this one, it follows the Westina. Okay. But now I recall that for compact spaces, this G index of the space X is finite if and only F is a local trivial principal boundary. I don't know if it's a paper in your paper with Gardella, or it was known earlier. I think probably Piotr. I don't know if I don't cite but that's certainly recalled in the paper with Dąbrowski.
Yeah, but it's not different.
Therefore, this theorem says that Baum, myself, and me, and Piotr conjecture holds whenever X is a locally trivial principal G boundary.
Yep.
This is a generalization is better than the previously known results about G's with non-trivial torsion, because if you have finite, first of all, because this is anti-hereditary property, so it suffices to check it for subgroups, particularly if there is a finite subgroup. It was known for subgroups, but if subgroup is finite, then the bundle is locally trivial always. G bundle is with finite subgroup, it's always locally trivial. So it suffices to assume this property, okay? Which is not, as far as I know, is not this case for the compact, for the quantum version of this conjecture. So now I pass precisely to this quantum non-commutative world, and we do this a la Gelfand-Naimark, extended slightly, by dualizing spaces to unit possibly non-commutative. G is dualized to compact quantum groups, possibly non-commutative algebras, which let me recall that I think Andrzej gave some definitions already, so let me remind you that this is a pair actually of SISSA algebra with a coproduct, so co-associative injective star homomorphism from H to the minimal tensor product of H with itself. Co-associativity means that you can act again by the coproduct here, identity here, or identity here, and this result is the same up to isomorphism. This coproduct should satisfy also the cancellation, which is a clever Voronovich generalization of the fact that there should be inverse in the group. Okay, so for quantum groups, we don't have antipode, which in general on the whole SISSA algebra you have it on the dense subalgebra, but this is the property which generalizes the cancellation of equivalent complex groups. Then we also take a free action, and this Andrzej already wrote, of this quantum group on a SISSA algebra A, called also coaction of this SISSA algebra H on A, which is an injective unital homomorphism from the algebra A to minimal tensor product of A with H, such that, well, co-associativity now, well, generalized co-associativity, there is no just coproduct, but also coaction, and coproduct is here. There is this co-unitality of Odlesh property that closed linear span of objects like that from A in A and H in H should be equal to the minimal tensor product of A with H. And the symmetric combination is actually something which only recently, let's say, I don't know exactly, 20 years probably, Elwood-Freeness condition, which was quite difficult to define Freeness condition for groups acting SISSA algebras and also for quantum groups systems, which is this condition quite symmetric with respect to the Polish unitality condition. As you see, again, you should get all minimal tensor product of A with H, taking this particular products of element A tensor identity from algebra A and coproduct co-multiplication of element B in the algebra, which is an element in A tensor A. And such structure we shall call quantum principal. If A is unital, we call it compact quantum principal H bundle. And right, okay, with the simplified notation per H coproduct just by H. There is also an analog of trivialization, global trivialization. It's dualization to the map, which I said equivariant map. So it's just now the map from the quantum group SISSA algebra H to the SISSA algebra A, on which H acts, which should be equivariant in the sense that it should interpret in this sense the coaction and the coproduct. In such a case, when there is a trivialization, we call coaction trivial and call also A the trivial H bundle, principal H bundle. Only recently, and there's the paper on preprint on the archive, it's yet, I think, not yet published. Gardel, Hayat, Dąbrowski, and Wu formulated a notion of locally trivial principal bundles, and it's done as follows. One should assume that there are number D, this natural number of equivariant, H equivariant in the sense which is here, star homomorphism, this time from rho 0 up to rho D, from the functions on the left open, right closed segment, tensor H to A, such that their sum, okay, equals to 1. There is also notion of so-called weak local triviality, which is invertive, and there is also another one which is strong, which I just mentioned at the end, just but I don't need it for today's talk. And the local triviality dimension of the action delta is just infimum of this numbers D, such a number of invariant equivariant star homomorphism. By the way, that also can be formulated as equivariant order 0 maps from H to A. That's another possible formulation.
CPC order 0 maps. CPC.
Well, some people order 0 just mean already that completely positive, but okay, completely positive. Yes.
Contractible.
Order contracted, okay, increasing norm equivariant maps. And infimum of such D, if there is no such a map, it's infinity, but it's so empty. But infimum of such D is called local triviality dimension. That's the one of these equivariant new dimensions which was introduced in this paper. By the way, so from this, it's just clear that delta is local trivial according to this statement. Precisely, this local triviality dimension of delta is finite. That, I think, requires small check that delta is trivial in this sense, okay, that there is such a variant, even only if the local triviality dimension is 0. Delta is, okay, I should say, actually, sorry, I should say this dimension, local triviality dimension, is not going under the equivalent C-star homomorphism. And in the classical case, when the algebra is continuous functions in a compact space and H is functions of a compact topological group.
Yes.
And there is I think you don't need freeness of this action here. Or maybe, okay, so let's assume free action R. And action of the quantum group H is taken just as a transposit, so just the pullback of this action R. The local triviality dimension of such action of this group on the algebra is just this classical index, the G index of the space X, which I defined in previous transparencies. And moreover, the local triviality dimension delta in this case is finite, if and only if it is a local trivial principal final boundary.
But Ludwig, local triviality implies freeness, so I think we are safe.
Okay, so you don't need to assume that R is free. Sorry, yes, that's right. Perfect. Now, we want to formulate this quantum Borsuk-Ulam generalization of conjecture, generalize the quantum Borsuk classical Borsuk-Ulam theorem. So for that, we consider now join of SISSA algebras. So this should be dually to this join of spaces, topological join. We use transparency. And unfortunately, the most natural one is most direct one when this corresponds to contracting either one space or the other space on two edges of on the interval. In this case, this corresponds dually to the evaluation at zero of the element here. So which result is here should stay in A, should be should stay in H. So it should be one on the some number, okay, in the algebra. And you could assume, you should assume maybe most naturally that the evaluation one should stay in A instead. But unfortunately, this doesn't admit the diagonal action and also doesn't admit pre-action. But as soon as you just make a so-called gauge or equivariant joint SISSA algebra and you assume that the result of evaluation of element here at the one is not just the element of A, but it's just the coaction of something in image of the coaction of the whole algebra A, then there is an action, and there is a diagonal action, and it's also free, can be shown free as soon as there's a free action of H on A, okay, of the compact quantum group. And this diagonal coaction is just the identity on the interval, functions on the interval. Okay, and just delta acting on H. And that's the conjecture. It generalizes very much the classical conjecture in two directions. Then you don't take just, you take also, so you take both space to be replaced by possibility of commutative SISSA algebra, and also the group we replace, we take a quantum group acting on algebra A. So we assuming a free action. So for a unital SISSA algebra with a free action delta on a non-trivial compact quantum group H delta, taking this equivariant join of the SISSA algebra with H, defined as here, with the induced free action as written as here, there are no H equivariant in the sense which I mentioned before, star homomorphism from the algebra A to this equivariant join of A in H. Of course, this arrow is dualizing previously we had from space join, topologically joined with group to space, but here is the arrow is going in the opposite direction because this contravariant dualization. And now there is a table, and maybe there are some arrows which should be both heads, okay? So that's this new quantum Borsuk-Ulam conjecture. There is no equivalent like that. It implies that there are no homomorphisms, star homomorphisms from A to the cone of A, which when evaluated at 1 are equivariant as maps from A to A. This implies now a version of Borough theorem that there is no such a gamma, maybe a modulo probably. Okay, so we have this statement as it is, and we call it, there is no such a map which evaluated at 1 is identity on the algebra A. And we call this A is not contracted. Now it's surprising that the inverse, which is classically true because we have points in the group G, we have unit in point G, is true only if there is a co-unit on this quantum group H. I mean, it's not, I mean, we don't know, maybe this is true also in some situations, but at least if there is a co-unit on the group H, we have also the inverse in this implication.
Mhm.
Also, there is a slight surprise about this quantum Borsuk-Ulam second theorem, conjecture number 2. Classically, there were maps from X join G to G. We claim also that there is no equivariant map from dually from H to the equivariant join. So I should put probably delta somewhere here, but okay, so I forgot to put deltas according to my notation definition. There's no equivariant map from H to the join, equivariant join, gauge join of A with H. And this follows from this statement follows from this statement if there is a character on the SISSA algebra, it should be A. I don't see that. Well, from this one, of course, if we take A plus H itself, this means that there is no equivariant map from H tensor join H, quantum join, gauge join to H, which means that this is non-trivial quantum principal binding, but this, I think, is still equivalent to the statement that
I believe so, yes.
Quantum.
Yeah, but here what is a crucial difference is that unlike in the classical case where we had this theorem from the 70s, I believe, that the only contractible compact house of topological group is the trivial group.
80s, it was quite late, actually, it was mid-80s. Yeah.
80s, not 70s? Okay, I thought it was like 73. But okay, that doesn't matter, it's 20th century.
Okay.
But we do not have such a statement in general, I believe, for compact quantum groups. And I think that the troublemakers might be simple SISSA. I'm not sure. Anyway, I'm not sure, but so we know that a large class of compact quantum groups is not contractible. This we know. So all these, quantum SE2s, everything that has classical subgroups with torsion, it's okay, right?
So now I come to the theorems. So this were about conjecture.
Yeah. But Ludwik, Ludwik, can you go back to the previous slide for just one more sec? Yeah. So when you now look here at this statement that you have, he has written correctly because you have the evaluation at 1 composed with gamma as equivariant. So that's what you missed in the classical setting. I mean, in the classical setting, this evaluation at 1 is just putting your space into its cone. Yeah. So here it's exactly as it should be. So
towards going to theorems, where they hold, where this conjecture, quantum Borsuk-Ulam conjecture holds, it's useful, convenient to analyze separately the cases when there are or not characters on A on H. So if there is no character both on A on H, there are no characters. So this conjecture so far we have for reduced SISSA algebras of 3 groups on and greater than 1 generators. If there is a character on A and no character on H, we actually suspect that there are no free actions, but we don't have this statement really checked. If there is no character on A, then there is character on Y, the conjecture holds trivially because given a character on H, we could produce a character on A, which is not possible. I mean, assume it not to be the case. So even for trivial compact quantum group, considering just C, okay. The irrational quantum torus is example of this situation with the standard action of the usual torus on 2 torus matrix algebras with n greater than 1 dimensional with Z modulo and Z action, cyclic action. The Kunz algebras of n with n greater than 1 with the gauge action and so on. So there are cases when there are no characters on A. So the mainstream situation when there are both, so this is kind of solved, okay, so the mainstream remains now both admit character, and this in particular contains the torsion case and the case of finite quantum groups with A plus A, okay. So in the best so far result, which I'm going to present, one of the assumptions employs this local triviality dimension, and in the proofs, I think uses the fact that there's been a local triviality dimension of for the equivariant join of A with H grows by 1 under this join with H. Anyway, grows. So that's this theorem. So one of these assumptions, so A is a unit of SISSA algebra with free action delta of a compact quantum group, H with coproduct delta. So it's mixed of these two theorems, where this one we had earlier, and this one is in this preprint on archive in the paper. Under still do work. Is that if H admits a torsion character, which is our assumption, equation, or a non-trivial classical subgroup of characters whose induced action is locally trivial in the sense of the local triviality dimension is finite, then the conjecture holds. There are no H equivariant star homomorphisms from A to the equivariant gauge join of A with H. So now this was in the classical situation when the group was finite, it was not necessary, it was just part of this assumption, but as far as I know, Piotr told me that there are examples of probably it's not clear that some action of quantum group with a torsion character that it might, there is I think example it may not to have a non-trivial classical subgroup of characters with locally trivial action and vice versa, I think. So this property you cannot remove, but also this property I think you cannot remove. So it's not clear for all quantum groups with torsion character that it has finite local triviality dimension. Okay. So applications of this, let me just briefly show that, for instance, from this follows, because of its corollaries, the non-contractibility of the Teplitz algebra, which admits a free action of Z0 to Z group, some of U1, even though the K theory of this Teplitz algebra is like the same as 2-4, is contractive. Q deformations of compact connected semi-simple Lie groups G, since they have always a torus of characters. A finite quantum group H, okay, separate, so it's not about, but the finite quantum group satisfies this conjecture, quantum Borsuk-Ulam Theorem, for in particular case when the H acts on itself, okay, and the coaction is just the coproduct. There are some other statements where I'm not quite sure if they fit to assumptions of the theorem. QBUT a few years ago checked that, for instance, in particular, reduced SISSA algebra of the is non-contractible. Gamma is discrete group that satisfies bound conjecture. But there is also stronger K-theoretic non-triviality result, not only non-triviality of bounding, but particular associated bounds. So let's say. Okay, with some particular representations of this principle for boundaries have non-trivial K theory. Okay, so for instance, this holds for this SISSA algebra of free group on any generators greater than 1. So this quantum Borsuk-Ulam conjecture remains still open, and there is a nice paper, the same paper which I just mentioned before, they observed that perhaps for solution there may be no really one well-behaved invariant for all free actions, in particular on finite perfect groups, compared to what we know about finite abelian groups. In particular, the local triviality dimension and also another one, spectral count, may both change under theta deformations, also change under theta deformations of groups and spaces, and also about taking full versus reduced SISSA algebra, and also finite quotients in the commutative situation. So for this reason, I think, okay, the new local triviality dimension plays important role in the studies, and it's worth studying further on its own. And actually, let me mention here that there are a few of them already. So there's local triviality dimension as I defined. There is another one which I mentioned also how it's defined, weak local triviality dimension. And the strong local triviality dimension is defined precisely by asking how you can map an algebra into multiple equivariant adjoint as I defined. There is also Rocklin dimension, but as far as I know, Piotr, please correct me, it's for group actions on SISSA algebras, it's not for quantum group actions. Anyway, there are some list of various new equivariant dimensions. And for them, the class of graph SISSA algebras is absolutely new and future testing ground. In particular, maybe possible that for this local dimension would be resolutive for this particular subclass of SISSA algebras, okay, and particular class of group actions of graph SISSA algebras. And let me recall, for example, that Waxman-Soberman quantum spheres of dimension are defined as quantum homogeneous spaces of the Voronowicz quantum SU and +1 groups with the antipodal Z modulo Z2Z action were shown to have local triviality dimension finite by using their presentation as graph SISSA algebras. So graph SISSA algebras should be studied, and they are helpful also for studying algebras which are isomorphic to graph SISSA algebras.
Ludwig, you realize we have minus 1 minute.
I finished. So this is in our project. So objectives are compute determine finiteness of local triviality dimension. One of them graph SISSA higher rank graph SISSA algebra study actions, more study actions on quantum groups, Tetris algebra, Kunz algebra, quantum length spaces, other cases. First steps should be applied. This what is already in the paper. And still under progress, where several tangent computation of the local triviality will take of them. Try to see if there is any pattern relating them to, I don't know, some data adjacent metrics or something like that. So try to get some pattern in this result. Next steps would be to use quantum symmetries from package 7 and do the same for quantum automorphism of graph SISSA algebras. As a warm exercise, I propose this. I don't know if you recognize what is this graph.
Yeah.
So it's self-referencing graph. Okay. Okay. Achieving these goals, I don't want to repeat it, will be useful to study, to get more structured graph SISSA algebras, and also for our leitmotif group action, Borsuk-Ulam Theorem conjecture for group actions, quantum group action of graph SISSA algebras. Thanks, buon anno, and keep non-trivial.
Ludwig, thank you so much. You stole our break. We have absolutely no time for questions. So thank you so much. I stop recording and we prepare the ground for the next speaker. Thanks.
Okay, thank you.